So welcome back. We had been discussing graphs of certain rational functions, and we determined that there are places where the graph shoots up to infinity. It could also go down to minus infinity. These forbidden values of x. These are what are called vertical asymptotes. Okay, if, as x is approaching some number, then the value of the graph is going either to plus or minus infinity. That looks something like this, or maybe something like this. Here the graph is going to plus infinity, here the graph is going to minus infinity, not as an end behavior. Okay. End behavior just means, oh, as x goes off and gets bigger and bigger. This is just end behavior. This is different. We're not talking about this now. What we're talking about right now is not as x goes off to infinity, as x approaches some number. So there's like some number, x equals c. And as x gets close, I have this shooting off to infinity or maybe off to minus infinity. So it's not eventually, it's not end behavior, it's at a specific value of x. This is called a vertical asymptote. Okay. The other definition on this slide, whoops, I didn't want highlighter, I wanted to get rid of everything. The other definition on this slide is horizontal asymptote, and that just says if the end behavior is going to a horizontal line. This is called a horizontal asymptote. So this part of the definition is end behavior, as x goes to infinity. End behavior, end behavior. This is end behavior because x is going to plus or minus infinity. This is not end behavior because it's as x goes to a specific number. Okay, and here's what they look like. Okay, so these first two pictures show horizontal asymptotes. As x goes to positive infinity in the first picture or negative infinity in the second, the graph is sort of squishing down and settling on a horizontal line. That is a horizontal asymptote. The sort of 90-degree rotation of that is as x approaches a specific number, y goes off to plus or minus infinity. That's a vertical asymptote. And in the first picture, we see it might do the same thing on both sides, infinity and infinity, or it might do opposite things, negative infinity on one side, positive infinity on another. They're both called vertical asymptotes. Okay, so how do we find where these vertical asymptotes and horizontal asymptotes are? So first, let's talk about vertical asymptotes. We've got a rational function, so p of x and q of x are both polynomials. However, now we have this term in lowest terms. What does this mean? So what we're doing is we're taking the notion of a rational number, a ratio of integers, like 6 over 7 or 2 over 9. This is an integer over an integer. But we're extending it to be integer powers of x over integer powers of x. That's what a rational function is. So think back to working with integers. I can write 3 over 4, but I can also write 6 over 8. And while they look different, they're not the same thing. Sorry, while they look different, they are the same thing because they're not written in lowest terms. 6 over 8 is 2 times 3 over 2 times 4. 2 over 2 is just 1, so I can cancel that off, and I'm just left with 3 over 4. In other words, if there was something I could factor out of the numerator and factor out of the denominator, then I should have canceled it off. That's what lowest term means here. Okay? Lowest terms means there is no common, okay, let me actually write it using letters. Lowest term means there are no common factors. Now remember, the numerator and denominator are both rational polynomials. Sorry, they're both polynomials. And now I want to know there isn't a factor that occurs in both of them. If it's there, then we need to be careful about it, maybe cancel it off. So how would I ever determine whether two polynomials have the same factor? That is exactly the same as not having any shared roots. Remember, roots of polynomials gives you factors. So if I want them to not have common factors, I want them to not have common roots. if you have this situation, I'm going to clear off my pen marks so we can focus on the original definition. If you have this situation where you are written in lowest terms, then exactly where you have zeros of the denominator is where you have vertical asymptotes. Okay? So as long as you have already found lowest terms, as long as you have already canceled off any shared factors, zeros of the denominator are vertical asymptotes. That's how you find them. So try to find vertical asymptotes, if there are any, of all of the following. So what you have to do is check to see if it's in lowest terms. Are there any shared factors? If there are not, just ask what are the roots of the denominator. If there are shared factors, cancel them off and then ask what are the roots of the denominator. So go ahead, pause, and do these four, and then we'll come back and do the solutions. Okay, so the numerator and denominator each have a single root of -5 and 3 respectively. There are no shared roots, so it's in lowest terms. That means x equals 3 is the only root of the denominator, and that is the only vertical asymptote. For b, the only root of the numerator is 0. The roots of the denominator are 7 and -7, so there are no shared roots. It's already in lowest terms. Therefore, 7 and -7 are vertical asymptotes. For c, the roots of the numerator are 0, and the denominator has no roots, so there are definitely no roots in common. Therefore, it has no vertical asymptotes. There are no roots of the denominator, so it just doesn't have any. That's fine. That can happen. And finally, how do I determine if they're in lowest terms? I have to find if there are any shared factors, if there are any common roots. Well, the numerator factors as x plus 5 times x minus 5, and the denominator as x plus 7 times x minus 5. So notice that there is a shared factor, which we cancel off. I want to put an asterisk here because we have to be a little careful about this. When I cancel that off, I get x plus 5 over x minus 7. Now it is in lowest terms, so x being -7 is the vertical asymptote. Okay, but let me take a step back and talk about what this asterisk means. So what did we do? Remember, when you cancel x minus 5 over x minus 5, you're saying this is equal to 1, so I don't need to bother writing it. That is true, except when x is equal to 5. Okay, so the function is equal to this as long as x isn't equal to 5. Otherwise, this step here would have been invalid. Okay, I can't cancel that off if x happens to be equal to 5. For any other value of x, this is fine. But what goes wrong if I try to let x equal 5? Here, x equals 5 is in the domain. I'd get 10 over 12, not an issue. Back here, x equals 5 is not in the domain. This is what goes wrong when you do this cancellation. You might be losing information about the domain. This is literally the only thing that happens when you do this cancellation, is that you lose some information about a single point that should have been excluded from the domain. The only difference between this function, I'll clear off pen marks. The only difference between this function and this one, these are exactly the same, except x equals 5 is not in the domain on the left. It is in the domain of the right. Other than that, the two graphs look identical. Okay, so if you tried to graph this, if you stick this into a graphing calculator, it's going to look like something like this. I'm just kind of estimating. Oh, come on, pen. Should look something like that. Okay, it's got a vertical asymptote at x equals -7. It has a horizontal asymptote at x equals 1, although we don't know how to find that yet, but that's why I've made this horizontal asymptote here at y equals 1. Sorry. That would be the graph of the thing on the right. If you graph the thing on the left, it's going to be exactly the same, except there's going to be a single hole in the graph. X equals 5 is just not allowed to be plugged in, So there is a hole missing from the graph. Everything else is exactly the same. There's just one missing value. But we were only asked in this part of the problem to find vertical asymptotes, so we reduce to lowest terms and then find things. Okay, so the only 0 of the denominator once reduced is -7, therefore that's the only vertical asymptote. If you started this problem and you just said factor this and find the roots, you would have accidentally said that x equals 5 is a vertical asymptote. It isn't, because these would have been canceled. Okay, so that's the one thing that can really throw you off in finding vertical asymptotes, this reduction to lowest terms. But take a break and we'll come back and keep doing more examples.